Good morning, everybody. As you know, today we're doing our very first podcast in honors geometry. This will replace my regular lectures and it will free up my time so that I will be able to work one-on-one with each and every one of you. I do hope you'll find these entertaining, but please recognize that my work in podcasts is literally a work in progress, and so there will be some bumps on the road, and bear with me on that. You should make sure that you have on hand your skeletal outline, and if you want to, you can also have the notebook for this section. I will have copies available for those of you who would like to use them. And feel free to take any extra notes that you might want to do on the side. After you're done with this lecture, then you are going to complete the assignments that I put on Learn, and which I will have copies of in class as well. Those should be practice A, practice B, and practice C unless I make a change, and that will be announced on Learn, and I will announce it in class. Again, I hope you enjoy this, and hopefully lots of good viewing. Thank you very much. Bye-bye now. Before we begin the triangle mid-segment theorem, I would ask that you make sure you have on hand two documents which you can use interchangeably or use together. One's the skeletal outline for 5-4, again, mid-segments of a triangle it's called, and the Know-It notebook for 5-4, the triangle mid-segment theorem. And as we go through the materials for today, I would ask that you record the information that I am telling you onto either or both of these documents. So for instance, for the objective in the Know-It notebook, there's a place for writing the lesson objective, and that is to prove and use properties of triangle mid-segments. Our vocabulary is mid-segment of a triangle, and again, there's a place for that in both the Know-It notebook and the skeletal outline. You can choose which one you wish to put in, and I would suggest you staple these together. It would be best to record the definition for the mid-segment of a triangle in the skeletal outline. There's a place for writing the definition, and then there's a blank triangle there that you can add information to here, as I will describe in a moment. First of all, in this space provided, please put in the definition of the mid-segment of a triangle. And a mid-segment of a triangle is a segment that joins the midpoints of two sides of the triangle. And because a triangle has three sides, then every triangle has three segments, which form in turn the mid-segment triangle. Now, if you will go to the blank triangle that you see on the skeletal outline, please fill in the information that you see on this slide before you for the triangle. So the vertices will be P, Q, and R. And then you will draw midpoints at X, Y, and Z. And then you will connect those midpoints with the mid-segments X, Y, Y, Z, and ZX. And so then you will have in turn an inner triangle, which would be triangle X, Y, Z. Also, please put in the tick marks that you see there. So the distance from Q to X and X to P will be congruent. That's one tick mark. The distance from P to Z and Z to R will be congruent. So they will have two tick marks. And the distance from Q to Y and Y to R will be congruent. And they have three tick marks. Our first example is going to examine two critical characteristics of midsegments and their corresponding sides. You remember each midsegment has a corresponding side of a triangle. So we're going to draw a triangle, triangle XYZ. And there really isn't enough room on the Know It notebook or the skeletal outline to draw this triangle. And in fact, the one on the skeletal outline is not the same one that's on this slide. So I would ask you to take a moment and pause this presentation, get out some paper so that you can draw this. And you don't have to use graph paper. If you have it, that's fine. But you can sketch it out, I think, fairly simply on a plain piece of paper. So the vertices of x, y, z will be at the following locations. X will have x and y coordinates of -1 and 8. Y will have x and y coordinates of 9 and 2. And z will have x and y coordinates of 3 and -4. M and N are the midpoints of line segment XZ and line segment YZ. Show that line segment MN is parallel to line segment XY and that line segment MN equals 1/2 of line segment XY. And those, of course, are the two critical properties. The first step we're going to use to do this is to find the coordinates of M and N. To do that, we're going to use the midpoint formula. And so we'll be looking for the midpoint of line segment XZ. And so doing that, we put in the X coordinates for X and Z, and those coordinates are -1 and +3. And since we're taking the average of those two coordinates, we divide by 2. And then we're taking the y coordinates of x and z, and those are 8 and -4. We're combining those, and again, because we're taking the average of those two numbers, we're dividing by 2. And therefore, the midpoint of x and z is 1, 2. All right, the next thing we need to do is to find the midpoint of YZ. Now, line segment YZ has, I should say the two points, Y and Z, have X coordinates of 9 and 3, so you'll combine those and again divide by 2. And the Y coordinates of YZ are 2 and -4, so you will combine those and divide by 2, and you will get midpoint coordinates for YZ of 6 and -1. The second step is to compare the slopes of line segment MN and XY. Now what we're going to do is we're going to find those slopes, and we're going to look to see if there's any relationship between the two. So to find the slope of line segment MN, again, we will use the coordinates of the 2 points that are the endpoints for line segment MN. And we are going to use the formula for slope, which is m equals y2 minus y1 divided by x2 minus x1. Now, the y coordinates for m and n are -1 and +2. So when we combine those in the formula, because we have a negative sign in the formula, then we will have -1 minus +2, or -1 minus 2, over the x coordinates, which are 6 and 1. So that will be 6 minus +1. And when we simplify that division problem or fraction, we will find that it's 3, actually -3 over 5. And that's the slope for MN. Now the slope of xy will require that we again use the slope formula, and the y coordinates for x and y are 2 and 8, and since we're subtracting those two coordinates, it's 2 minus positive 8, and then that will be divided by or over the x coordinates of 9 and negative 1. So in this case we will have 9 minus negative 1, which is the same as, of course, 9 plus 1. So simplifying, again, our slope is going to be negative 3 over 5. So the important thing now is that we found that the slopes are the same. And because the slopes are the same, then line segment MN is parallel to line segment XY. Step 3. In step 3, we compare the heights or lengths, really, of line segments MN and XY. And we're going to use the distance formula to do that. And if you remember, the distance formula was d equals, and then we used the radical sign or square root sign, as I sometimes call it, with the following information inside of it. And that information is parentheses x sub 2 minus x sub 1 in parentheses squared plus y sub 2 minus y sub 1 parentheses squared. So now what we're going to do is we're going to use that formula, and we're going to plug in the coordinates for the endpoints for MN. So in doing that, we will get the square root of, and in parentheses underneath it will be the y coordinates, which are 6 and 1. So parentheses 6 minus 1 in parentheses squared, plus the x coordinates of M and N, which are negative 1 and 2. So we're going to have parentheses negative 1 minus 2 in parentheses squared. When you combine those two x and y sets of x and y coordinates and square them and add them together, you get the square root of 34. Now that's not a perfect square, but we're going to leave that alone for the moment, and we are going to find the distance or length of line segment XY. So I've now put that on screen for you, and you will see that the x coordinates for line segment XY are 9 and negative 1, and for the y coordinates they are 2 and 8. So your formula will read the square root of, and then in parentheses 9 minus, and then in a sub parentheses, inner parentheses, negative 1 in parentheses, all squared, plus in parentheses 2 minus 8 in parentheses squared. And again, when you combine the x coordinates and square them, and you combine the y coordinates and square them, and then add those sums together and take the square root of them and simplify, you get 2 square root of 34. So now think about this a second. Even though you're dealing with the square root of 34, M and N is actually half of the length of xy, because xy is 2 times the square root of 34. So since the square root of 34 equals 1/2 of 2 times the square root of 34, then mn equals 1/2 of xy. Now show the following in your notes on your own. Based upon the previous two examples, you should be able to see that a midsegment is always parallel to its corresponding side, and that midsegments are 1/2 the length of their corresponding sides. This gives rise to the triangle midsegment theorem, which is theorem 5-4-1. And I would like you to reproduce this, or write it, in other words, on the bottom of the first page of the skeletal outline where it says theorem 5-4-1. If the blanks aren't exactly correct, please just simply change the wording so that it matches what is on this screen. And that wording is that a midsegment of a triangle is parallel to a side of the triangle and its length is half the length of that side. Now, I would also like you to draw above that theorem in a blank spot there, if you can, the triangle that you see in this midsegment theorem, triangle ABC. And it has a actually has midpoints identified. The midpoint of AB is D, and the midpoint of BC is E. And please draw a midsegment from D to E and show that correspondingly the line segment AB is broken into two congruent parts, and that line segment BC is broken into two congruent parts. And please use the tick marks shown there. In example 2a, we are going to use the triangle midsegment theorem to determine the measure of certain lengths of line segments and angles. And the triangle that you see on the slide here can also be found at the very bottom of the skeletal outline, page 1. But that triangle is inverted, so turn your page upside down and you'll see that triangle roughly in the same form as the one that's found on the slide. But the letters are different. So change the letters of the triangle that's on your page that's upside down to the ones shown here in the slide. So the basic triangle, the large triangle, is ACE, and the inner smaller triangle, which is formed from the midsegments, is BDF. And fill in the values involved. So F to D is 6.2 units, and angle BDF is 26 degrees. Now the first thing we're going to do is find the measure of BD. So we're going to set this up as a proof, and we're going to use the midsegment theorem as the reason for being able to find the measure BD. So in this case, the midsegment theorem is going to say that line segment BD is equal to 1/2 of the base, which is line segment AE. And AE is already identified as 17 units. So we're going to substitute 17 for AE. And when we do that and simplify, you're going to find that line segment BD, which is the midsegment, is 8.5 units. In the next example, we're going to use the same triangle, but this time we're going to find the measure of angle CBD. Now the only angle that we have measure for is angle BDF, but angle BDF is across the line segment BD and on the opposite side of angle CBD. So what we're going to do is prove that angle CBD is going to be 26 degrees in measure, just like angle BDF. Now to do that, we're going to use the midsegment theorem, and we're going to first of all show that line segment DF, which is a midsection, is parallel to its corresponding base, which is line segment CA. And to do so will show us that we have a midsegment. And then because they're parallel, we're able to show that the line segment BD acts as a transversal, and as it crosses the two parallel lines DF and CA. And because it is a transversal, then you have alternate interior angles, and those angles are congruent, and those angles are, again, BDF, and the angle we're looking for, CBD. So we can say that the measure of angle CBD equals the measure of BDF. We'll substitute the 26 degrees for the measure of BDF, and we find out that the measure of angle CBD is 26 degrees. All right, next I'd ask you to, in the next example, solve for JL. as you know, from time to time, students complain that they don't see the practical aspects of many of the theorems that are in geometry. Uh, However, the triangle midsegment theorem really demonstrates great practical application in that it allows us to indirectly measure distances that we could not measure directly due to some obstruction. So let's see an example of that. I have on the right of this particular slide a cross-section of an A-frame. And you see A-frames in construction all the time. A lot of times they're used for cabins, such as ones that you see up in Mount Lemmon. And let's just suppose that we tilted up the sides of our A-frame. Those would be the sides PS and QT before we actually measured the length of the truss that we would need to go in between. That would be the line segment ST. Well, if we knew that ST was uh, at the midpoint of PS and QT, and that it was therefore the midsection, then we know that we could measure the distance of PQ at the floor very easily and just divide by 2 and we would have the correct distance or length of ST. So we're going to use the midsegment, the triangle midsegment theorem, and we know that because of it, ST equals 1/2 the distance or length of PQ. And since we know that PQ is 46 inches, we're going to substitute that. And we're going to simplify, and we're therefore going to find out that the length of the support ST is 23 inches. So there you have it, practical application for the use of the triangle midsegment theorem. And this concludes our lecture on midsegments. So 5-4 is complete. And you now need to go to the assignments that I have inserted into Learn that we're going to do today. So those would be in-class assignments. I've printed those out. Those will be practice A, practice B, and practice C. And I want you to work in groups, and I will have given you instructions in regards to setting those groups up. And we'll go around and work with you, making sure that you understand the principles that are in this lecture. Thank you very much.